Guys, I want to show you something really quick here, and that's the project I worked on a while back. It's called Azure Stream Analytics, and it's geospatial indexing. All right, so what is Azure Stream Analytics? It is a real-time complex event processing engine, very much like Apache Flink. The engine receives multiple streams of data, and including static reference data, and it processes it using a temporal SQL. And by the temporal, I mean the events have timestamp and the SQL has a window capability. So instead of having tables, you have windowing. So you can see the set of events from the beginning to the end of time. It is a fully managed cloud distributed service in Azure, easy to provision and very easy to run. And the geospatial problems that we had is like this is three scenarios, customer scenarios that they have. uh, One was NASCAR. NASCAR wants to monitor in real time the vehicles during the race. And every time a car enters the pit lane, they want to monitor the speed. So if the car goes over the speed limit for the pit, they would receive an event. Another one was the construction site, machinery reporting GPS. It was reporting GPS data, and they want to monitor if the machine leaves the construction site. So this is also a geofence problem. The last one is taxi fleet monitoring. They want to do price matching, and by that I mean they have the total earnings of the taxi versus how much the taxi is running through the city. They have some percentage that is acceptable because sometimes the taxi has to reposition itself for better trips. It has to put gas, so they want to keep a look on that. All right. So then, what is a temporal SQL? This is looks the same as SQL. I have the select of the position and speed of the car from the telemetry stream. They partition by the car number, and then you can parallelize the computation. You join by reference data on the condition of the car is inside of the pit lane, and then the on and the function here are the geospatial features. All right. So then, how do we solve this problem? We need a geometry and geography library, which is SQL types. We have to think about scaling this for millions of edges and thousands of fences. We have to account real-time streaming data. And the one thing good about geofencing or geospatial problems is one side usually of the join is usually either static or slow moving. And by static, I mean it's a working side, it's a state, or it's a pit lane, it's a building. Or slowly moving is a temporal SQL query, which divides the stream in windows. Users usually do 30 minutes, 1 hour, couple days, and that is the slowly moving. So the index has the opportunity to work during that time, so it doesn't overpower the competition. And ASA needs a spatial index for doing cross join performance. All right, so this is couple of indexes that do geospatial. Couple candidates. I'll have grid index, very simple to implement, but it lacks granularity and you have to set it. It's not good for dynamic data. Z order, very good for sequential searches, but lacks precision. The KD3 is good for the K nearest neighbor, but bad for rebalancing and different types of geometries. And by different types, we have polygons, we have multi-polygons, which are separate in space, and then polygons with holes on it. Uh, Quad tree, octet tree is very good for uniform distributed data, but unbalanced spaces not doesn't do so well. And R3 or R star tree, really good for dynamic data. So it works on the static, it works on the streams, very good for insertion, deletion. And as long as we minimize the overlap of the bounding boxes, the insertion, deletion, and search, split and merge, they all log in. All right. So visually, what is a index? The R3 or index looks like. This is what looks like. So where you have a clustered items, you have a lot of bounding boxes, and who has less clustered items, you have larger bounding boxes and no bounding boxes or nothing to search where there's nothing. That's what you expect. And here you have some overlaps or a lot of overlaps where you have a lot of items. And then how do we minimize this? So as long as you minimize the overlaps, log n computation for everything. And there are usually three different types of um, insertion and splitting, which is quadratic, linear, and R star. And we're going to look at those. The quadratic has these artifacts which are longitudinal, very long, very thin artifacts. And the reason here is you have 360 degrees for longitudes and 180 degrees for latitude. So every meter that you have a longitudinal meter is it values double on the area when doing the computation for the split than 1 meter latitudinal meter. So as it looks for the largest increase of area, it's always going to pick longitudinal areas, a longitudinal large bounding box, because that gives you the largest area. And this gets worse when you go to the poles. So to kind of try to solve this problem, there is the linear case, which doesn't really solve. You end up with both now. You have longitudinal artifacts and latitudinal artifacts. The best one, it comes with some more overhead for the computation, but this is what you would expect for a well-behaved index. So you have the R star. You have three types of things that are used for computing the bounding box. The first one is minimal overlaps of the bounding box, so the computation stays log n. Minimal area and minimum margin. So it uses these three numbers to compute the bounding box. And as you can see, you still have very clustered elements on one side. The bounding box are very small. There's going to be more search there. Where you have more sparse data, then you have the a larger bounding box and less bounding boxes, and they are very well distributed. There is very little you know, overlap. And the reason here is there is one thing more on the algorithm when you try to insert an item. If you insert an item inside of a bounding box that is over the threshold of the size of the bounding box, then you have a p% of nodes that you remove from that bounding box and try to reinsert them again. And the idea is, instead of just splitting right away, we remove a certain percentage, usually 30% of the items, and insert again on the tree. So it has the chance to redistribute it itself on already existing bounding boxes. So you don't need to split, and it's less computation. This is the paper I used for doing this research, and it has all this information of different algorithms for splitting, and also has a pseudo algorithm how to do everything. So the search and remove, insert, etc. So I will leave a link on the description below.